In today's lesson, we are going to cover simple probabilities as well as theoretical probability. So our main goals today is to understand or be able to measure and calculate simple probability, as well as be able to determine odds and theoretical probability. So the first thing we're going to look at is experimental probability. It's probably the simplest ones. And in order to look at this, we are going to look at a little bit of an interactive game that you can find on the actual course website. So if you go to the games fair, in general, it's kind of like an overall arcade game, or carnival game. You don't have to really worry too much about this if we're just going to go into play the games. You can always control the sound. So the game that we're going to play today is the dice roller game, or the die roller. So basically the way it works, each roll of the die costs 10 points, and if you win, or you win 50 points if you roll a 6. So all you're doing is basically rolling a dice, and it's going to record the number of times that you get a certain roll. So we're just going to roll. So we lost points, and we're just going to keep on playing, and we're going to do this a bunch of different times. So we haven't won yet. Oh, we won once. So you can keep on doing this as many times if you want. I'm going to stop there, but you can play as many times as you want just to get into it. And what we're going to do, or what you're going to do after that, is you're going to think about, what did you notice as you were playing the game? Or what do you wonder? Is there anything you think about as you're playing the game? And when you're done, make sure you record that occurrence frequency table in your notes, because we are going to revisit this. So what is probability? Well, probability strategies are used constantly in day-to-day life to help us with decisions. So you may think of it as maybe the chance of rain, or the chance that there's going to be traffic, or anything like that. And I'm sure you can think of a few other ones where probability could come into play. Probability, as a definition, is the likelihood of an event occurring. So how likely is an event going to happen? An experimental probability, this is our formula. PA equals NA over NT. And quite simply, what this is referring to, PA is the probability that outcome A occurs. NA is the number of times A occurs, or occurred. And T, or NT, is the total number of trials. So essentially, experimental probability is basically what did happen. So if we do an experiment, or we run trials similar to the dice roller game, we rolled the die a number of times, and that is our number of trials. And then if we want to find out the probability that something happens, we just have to determine what we're trying to look for, and that's going to be our outcome A, and then we look for the number of times that value occurred. So for example, if we go back to our dice roller game, if we bring it back up just to see what our numbers are. So if you didn't copy this down, again, if you do this on your own, you may get different numbers, but essentially you're copying down this table here into your notes. So copying it down, we want to determine the experimental probability of each roll. So what is the experimental probability that we are going to roll a 1, a 2, a 3, a 4, a 5, or a 6? The first thing we do want to do is figure out the total. What is the total number of trials? How many times did we roll this, or roll this dice? So we're adding up the frequency. So 3 plus 2 plus 1 is 6, 10, 11. So the total numbers of times that we rolled the dice, or the die, would be 11 times. So that's our NT. Our NA all depends on what outcome we're looking at. So for example, I'll do the long form way. If we're looking for the probability of getting a 1, we want to look for the number of times 1 occurs over the total number of trials which is NT. So in this case, the probability of getting 1 is going to be 3 over 11. So that's the probability of getting rolling a 1. And again, you could reduce this fraction if you want to try to reduce the fraction if you can. In this case, you can't. You could turn it to a decimal, and then you could also turn it to a percent. If we do the probability of rolling a 2, you're looking for the number of times 2 occurred over the total number of trials. So in this case, the probability of rolling a 2 was 2 out of 11. We can't reduce that any further. And as a decimal, we get 0.18 or 18%. And again, we can do this for all of them, or that we want to do it for all of them. So 3 would be 1 over 11. Probability of getting a 4 would be 0 out of 11, or just 0. Probability of rolling a 5 would be 4 out of 11. The probability of rolling a 6 equals 1 out of 11. So what could we do with this information? Well, if we wanted to use this information, if we only win when we roll a 6, we would use this information to see, is it likely that I'm going to win? Based on what I've rolled, is it likely that I'm going to win? And you could look at your probabilities for each one, and you would probably say that, you know what, it's not likely that I'm going to win, so maybe I'm not going to play this game. So that's what you're going to use the probabilities for. You're going to look, if your goal is to win, which it should be, you want to get points. How could you use information? Well, you could ask the question, is it likely I'm going to win? Or you could think of, should I be playing this game? Do I want to play this game? Something along those lines. Another example, so this one's going to be hypothetical. Normally we would ask the class, but obviously right now I'm recording this by myself. So which chocolate bar would you prefer? So let's say we do this in the class. We ask the question. We get 5 people would prefer a caramel. 8 people prefer a Kit Kat. 7 people prefer a Snickers. And 9 people prefer a Reese's Cup. So 5, 8, 7, and 9. So again, all hypothetical. In our actual notes, we would have something different, but really it doesn't really matter in this case. So I want to determine, again, the experimental probability of each chocolate bar. So if I go back up and I look at my table, or if I zoom out a bit so I can see both. So the probability of a caramel is going to equal how many times a caramel occurred. In this case, it was 5, over the total number of trials, or in this case, the total number of participants. So if we have 5, 8, 7, 9, we have 29 people. So in this case, the probability is 5 out of 29. Can't really reduce that nicely. We can turn it into a decimal, which is 0.172. So basically we just divided, and then we can turn this into a percent by multiplying by 100. So the probability of getting a caramel is 17.2%, or the experimental probability of picking someone that likes caramel is 17.2%. Probability of a Kit Kat, again, same idea. How many times did Kit Kat occur? In this case, 8 times out of 29. Again, we can't reduce it to a nice fraction. We can turn it to a decimal, and we can turn that into a percent of 27.6%. And again, same idea through the rest of them. How many times they occurred over the number of trials, or in this case, the number of people that we asked. 24.1% chance of Snickers. And the last one for Reese's, 9 out of 29, or 0.310, 31% chance. So that's the experimental probability of each chocolate bar. If we look at it, based on these results, how could I use this information? Well, if I'm asking this as a teacher and I'm asking the class, how can I use this? I would use this to determine which chocolate bars I should buy as maybe prizes. So I should buy Reese's Cups and Kit Kats as prizes. Basically, I'm just trying to say the most ones that are likely to occur are probably the most ones that are going to get chosen. So if I wanted to buy, I should get more of them. Or if I just wanted to buy some for the class, that's what I should be buying. The next thing we're going to look at is theoretical probability and odds. So it's going to be very similar to experimental probability, although there's going to be a slight difference. But before we get into that, just going to talk about today's code word. So today's code word for this lesson is going to be ice. Again, the code word is ice. So back to the lesson, theoretical probability and odds. So theoretical probability is the likelihood of all possible outcomes. And if you look at this formula, it looks almost identical. The only difference is the bottom part of our fraction or our denominator, which is ns instead of nt. And ns basically stands for the set of all possible outcomes. So basically, if I'm looking at a scenario, what are all the outcomes that I could have? NA is still the number of times A occurs or event A, and PA is still the probability of outcome A. The difference between theoretical and experimental, theoretical, it's kind of in the name. This is what should happen. So experimental was what did happen. Theoretical is what should happen. It's all based on theory. It's based on what the possible outcomes are and what event I'm looking at. So it's what should happen. So for example, we're going to look at the first one. We're going to look at rolling a pair of dice. So we have two pairs of dice here. We want to fill out this chart to fill out the outcome. So for example, 1 and 1, I get a sum of 2. 2 and 1, I get 3. 1 and 2, I get 3, and so on. So again, take a couple minutes or a minute or two, fill this out on your own, and we're going to come back. So once you filled out the table, it should look like this. Again, these are all the possible sums or combinations that you could get when rolling two pairs or a pair of dice. So what we want to do is, using this, we want to determine the theoretical probability of each outcome when rolling a pair of dice. So if I look at the first one, P6. So this is rolling a 6. So what is the probability of rolling a 6, or a sum of 6 in this case? So if I go back and I look at this, there's a couple things I need to know. One, I need to know the number of times 6 can occur, and one, I need to know the set of outcomes, or how many outcomes I have. So in this case, easy one to figure out first is the number of times 6 occurs. So I look through my chart, I see that 6 occurs 1, 2, 3, 4, 5 times. So 6 occurs 5 times. Now what is the total number of outcomes? You may think, well, there's 11 different numbers, 2 to 12. So that means the total number of possible outcomes is 12. However, each combination of each of the two die, so each square is considered an outcome in this case. So in this case, there are 36 total possible outcomes. So here, the probability of rolling a 6 is 5 over 36. We can't reduce that, but we can turn it into a decimal of 0.138, which we can then turn into a percent, which is 13.8%. So again, the format is still the same, even though we're looking at theoretical probability instead of experimental. For B, we're looking for P less than 10, or less than or equal to 10. Sorry, not less than, greater than or equal to 10, because if it's the option that we're looking for is being eaten by the sign, or you could say, or 10 is not being eaten, so it's considered less than. So essentially what this is saying is, what is the probability of at least 10? So any of these values can be 10 or greater. So if I go back up to my chart, I'm looking for the number of times that it's at least 10 or greater over the total number, or the set of outcomes, or the total number of possible outcomes, which we know it's going to stay the same as the last one. It's still going to be 36. That doesn't change because the number of outcomes doesn't change theoretically. And now all we need to do is figure out, well, how many outcomes are at least 10 or greater? So in this case, if I look through my chart, I see 1, 2, 3, 4, 5, 6. So I only see 6 outcomes that are 10 or greater. I can reduce this fraction to 1 over 6. I can turn that into a decimal, a decimal of 0.16. We can say 167 because it's 1.6 repeating. And then this turns into a fraction, 16.7. So this is, the probability of rolling a number that is at least 10 or greater is 16.7%. In example 2, we're looking at now a different scenario. A coin is tossed 4 times. What is the probability of getting exactly 2 heads? So in this case, because we're seeing different outcomes occur, it may be helpful to create a tree diagram to see exactly what we're looking at. So for example, I flip the coin once. My outcomes are either a head or a tail. Flip the coin again, my outcomes are either a head or a tail off of each outcome. Because I could flip a head first and then a head again, or a head first and then a tail, and the same thing on the other side. And you're going to repeat that step off of each one. So that's 1 flip, 2 flip, 3 flips, 4 flips again on the last set. And it can get a little messy if you don't space things out properly, as we can see. But essentially that is the main idea. So getting exactly 2 heads. So if I want to figure this out, I'm going to look at all of my different pathways. Keep in mind, one outcome is one entire pathway going from start to finish. So it's not just wherever we decide to stop. It goes from the start to the finish, or you could look entirely at the bottom. I'm going to move this over a bit. So an easy way to figure this out, or to figure out the number of outcomes, so probability of 2 heads, we're looking for the number of times 2 heads occurs over the total set of outcomes, or the total number of possible outcomes. So to figure out the total number of possible outcomes, from the tree diagram, I'm going to count the very last row. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that is the total number of possible outcomes, or the total number of branches or pathways that I could take. Now, in order to figure out the number of times I can get exactly 2 heads, I'm going to have to follow my pathways. So there's 1, 2, 3, 4, 5, and 6. So there's 6 ways I can get exactly 2 heads. So n, or the number of times I can do it, is 6. So my percentage, or my probability, is 6 over 16. This I can reduce dividing by 2, so I can get 3 over 8, which I can turn into a decimal if I wish. 0.375, which also equals 37.5%. So if I flip a coin 4 times, there's a 37.5% chance that I will be getting exactly 2 heads. What is the probability of getting at least 1 head? So this one I'm going to leave blank because there are multiple ways that you can do this, and we are going to look at them on the next slide. So I want you to try and come up with your own solution for this, because there are multiple ways of solving this question. So I'm going to pause the video and I'm going to come up with the exact answer, but again, try this one on your own. So going through and solving this, you should get that it's a 15 over 16 probability of getting at least 1 head, which works out to about 93.75%. So you may have solved it one way, but there are actually 2 ways that you can solve this. So if you solved it one way, hopefully you tried to think about at least another way to solve it. If not, we are going to look at both ways, because it will be helpful to know both methods. So there is what we call the direct way versus the indirect way. So if we're looking at the direct way, the direct method is to basically look for what I'm solving for, or look for the outcomes that I'm looking for. So if I know that the probability of at least 1 head, I'm going to go through my chart, go through my tree diagram, and count all the ways I can get at least 1 head. In this case, that's where I get the 15 out of 16, or the 93.75%. The indirect method is where you subtract the impossible case from 1. So there's a couple things we need to think about here. The reason that we're looking or subtracting it from 1 is 1, all probabilities equal 1 or 100%. So that is the most probable that you can be when you're looking at outcomes. The impossible case, this is what we refer to with the PA with the apostrophe. You could also call it the complement. So it's also known as the complement or not A. So what is the probability of not A? So in this case, if all probabilities have to add up to 1 or 100%, then if we look at the first equation here, the probability of what we're looking for plus the probability of what we're not looking for, so every other possible outcome, that would have to equal 1. We use our algebra, rearrange the equation, solve for what we're actually looking for, the probability of A. It's 1 minus the probability of not A. So in this case, if I'm looking for the probability of at least one head, then I'm going to do 1 minus the probability of not getting a head. And the only way I could not get a head would be if I get all tails, so the complement, or if we want to rewrite it just to kind of show where this is coming from. So I'm going to say 4 tails, or all tails. That's the only outcome. And if we go back to our table, there's only one outcome where we can get 4 tails. 1 minus 1 over 16, which is equals 15 over 16. So that's the indirect method. Right? It's a lot easier sometimes in some cases, depending on what we're looking at, to figure out the complement, or not A, rather than the probability of A. So in example 3, we want to use the indirect method of determining the probability of not drawing an ace from a deck of cards. So the probability, we'll just say, of no or not an ace is going to equal, if we're using the indirect method, it's going to be 1 minus the probability of, we want to write it out, everything but an ace. Wait, no, sorry. Not the probability of everything but ace. That's what we're actually looking for. So the probability of getting an ace, because that's the complement to not an ace. So it's going to be 1 minus, well, what's the probability of getting an ace? If we look at our deck of cards here, we can see that there are 4 aces in a deck of 52 cards. So 1 minus 4 over 52. If we were subtracting fractions, we want to get the same denominator. 52 over 52 minus 4 over 52. So we get the probability of not getting an ace is 48 over 52. Which, if we want to reduce it, we can to 12 over 13, which we can turn into a fraction or a decimal of 0.923 or 92.3%. So there's a 92.3% chance of not getting an ace. And again, that's the indirect method that we just did. Using that same idea, what we're going to look at are the odds. So the odds is something, a term you might see. You might hear the odds of winning something, the odds of getting something, the odds of someone winning, or the odds of an outcome happening. And usually the two terms are odds in favor of event A or odds against event A. So the two situations, odds in favor of A are, or the formula is, the probability of A as a ratio to the probability of not A, or the complement of A. And the odds against, we put the probability of not getting A as a ratio to the probability of getting A. So basically it's just ordering the two pairs. If it's in favor, it's what's the probability of getting it comes first. If it's against, what's the complement that comes first. So a card is selected at random from a deck of cards. What is the probability of drawing a spade? Well, the probability of drawing a spade, if we know our deck of cards, a spade is 1 suit out of 4. So you could say 13 out of 52, or 1 over 4. There's 1 suit out of 4 possible suits, essentially. What is the probability of not drawing a spade? Well, in this case, we can do the indirect method. We could subtract it from 1. So if we subtract 13 over 52 from 1, we would get 39 over 52, which basically works out to 3 over 4. Because there's 3 other suits out of 4 that you could pick. Essentially, that's what it breaks down to. So what are the odds in favor of drawing a spade? Well, for setting up a ratio, the probability of getting a spade to the probability of the complement. We want to break this down. The probability of a spade set up as a ratio to the probability of a not spade. And this would break down to 1 over 4 to 3 over 4, which if you really wanted to, you could convert it to basically just saying 1 to 3. So the odds in favor of drawing a spade are 1 to 3. What are the odds against drawing a spade? Well, we could go through the same steps. Probability of A complement, the probability of A, well, it's not spade to spades. 3 over 4 is the probability of not spades to 1 over 4. And it just basically reverses. So it's just the same two numbers, but just flipped. Because again, it's the against. So the odds against drawing a spade are 3 to 1. So that basically covers looking at experimental probability, theoretical probability, and looking at odds. So those are the main things that you should be looking at. Hopefully it's not too complicated. Essentially, it's the same formula. You're just looking at either theoretically what should happen or experimentally what did happen. But the formula is the same thing, essentially, when you break it down. And then odds are just comparing two probabilities in a ratio. But again, work through the following homework questions from the textbook. And if you have any questions, again, or you need help, please, again, go back, start reviewing through the notes, and then you can always get in touch with me.